A nuclear reactor once decided whether 100,000 people lived or froze to death. Not during a meltdown, not during war, but every single winter, deep in Siberia. One reactor ran non-stop for decades, not because the Soviet Union needed more plutonium, but because an entire city depended on its heat to survive -40-degree winters. The problem was where that reactor lived. It wasn't built in the open. It had no cooling towers, no natural airflow. It was buried 200 meters inside a solid mountain. Inside that rock, it produced enough heat to boil a lake dry in minutes. If cooling failed, fuel would melt, graphite could ignite, and the mountain would trap the fire with nowhere for the heat to escape. This machine was never designed to save lives. It was built to make weapons. Yet somehow, Soviet engineers turned it into the heart of a city. And once that happened, letting it fail was no longer an option. By the time most people learned this reactor existed, it had already been running for decades. But the city that depended on it had no such luxury. Every winter, survival was negotiated day by day, hour by hour, through steel pipes carrying heat from deep inside a mountain. This wasn't a military base in the traditional sense. It was a city's schools, apartments, hospitals, factories built in one of the coldest inhabited regions on Earth. In winter, temperatures didn't dip below freezing. They stayed there, -30, -40, for months. In those conditions, heat wasn't comfort. It was life support. If district heating failed, water pipes would freeze solid within hours. Radiators would crack. Electrical systems would follow. Hospitals would lose temperature control. And once buildings froze, reheating them wasn't simple. Walls split. Foundations fractured. Entire blocks became uninhabitable. For cities in Siberia, heating failure wasn't an inconvenience. It was a cascade. And for this city, known for decades only by a postal code, there was no backup plan. Because the heat came from one place, 200 meters below ground, inside a mountain of solid granite, a nuclear reactor ran continuously, day and night. Not seasonally, not intermittently, continuously. That reactor was never intended to carry that responsibility. When it was conceived, the goal was simple and brutal: produce plutonium for atomic weapons as fast and as reliably as possible. Heat was a byproduct. Waste heat to be discarded. But geography changed everything. The Soviet leadership had chosen this site in central Siberia for secrecy and protection. American bombers could not reach it. Granite could not be pierced easily. And rivers flowing through the region could, in theory, provide cooling water. What planners didn't design for, at least not at first, was what happened after the reactor turned on and a city began to grow above it. Workers arrived. Then their families. Schools were built. Housing blocks followed. Infrastructure spread outward from the mountain. And with every apartment connected to the heating grid, the reactor below became less optional. By the early 1960s, tens of thousands of people depended on that heat every winter. Failure was no longer a technical problem. It was a humanitarian one. But keeping a nuclear reactor alive underground in Siberia was not a solved problem. No one had done it before, and no one had done it at this scale. The reactor produced over 1,000 megawatts of thermal energy, enough heat to vaporize massive quantities of water in minutes. In normal nuclear facilities, that heat was managed with towering cooling structures, open airflow, and easy access to water sources. Here, none of that existed. The reactor was sealed inside a mountain. Airflow was controlled. Every tunnel was deliberate. Every pipe was embedded in rock. Heat had nowhere to go unless engineers forced it out, step by step, through systems that could not fail. If cooling stopped, fuel elements would overheat rapidly. Aluminum cladding would weaken. Uranium would deform. And inside a confined underground space, heat wouldn't dissipate. It would accumulate. Worse still, the reactor's graphite core used to slow neutrons, absorbed radiation energy, and heated up independently. If graphite overheated, it didn't just melt, it burned. Graphite fires are among the most dangerous events in nuclear engineering. They are difficult to extinguish, capable of spreading rapidly, and able to release radioactive material into surrounding spaces. Inside a mountain, a graphite fire would be catastrophic. There would be no open sky for heat to escape into, no atmosphere to vent into safely. The mountain itself would trap the disaster. And yet, this reactor could not be allowed to shut down. Not in January, not in February, not when the city above depended on it to stay alive. This was the paradox Soviet engineers faced. A machine built to fuel the Cold War had quietly become the heart of a civilian city. Its mission had expanded beyond weapons. It now had to provide electricity, and more critically, it had to provide heat day after day, year after year, through some of the harshest winters on the planet. But there was another problem. The first reactors at this site had already shown what happened when cooling was handled carelessly. Early designs had taken the simplest route: pump river water through the reactor once, then dump it back. It worked, but the river paid the price. Downstream contamination, mysterious illnesses, environmental damage that could no longer be ignored even in a system built on secrecy. By the time engineers began planning the next reactor, the mandate had changed. This time, failure wasn't acceptable. Dumping radioactive water wasn't acceptable. And wasting heat, when an entire city was freezing above, was no longer acceptable either. What Soviet engineers were being asked to build wasn't just a reactor. It was a closed, self-contained life support system for a city, buried inside a mountain, running on 1,960 seconds technology in Siberia. And once construction began, there would be no second chances. Before engineers tried to save a city with a reactor, they almost destroyed a river. The first reactors built inside this Siberian mountain were designed under a different kind of pressure. Speed mattered more than consequences. Plutonium production had to be fast, reliable, continuous. Everything else was secondary. Cooling, in particular, was treated as a problem with an obvious answer. There was a river nearby, one of Siberia's great rivers, wide, cold, and seemingly endless. Engineers pumped water straight from it, ran that water through the reactor core once, and then released it back downstream. From a purely mechanical standpoint, it worked. Heat was removed. Fuel stayed intact. The reactor kept producing plutonium, but what flowed back into the river was no longer just water. It carried radioactive contamination, invisible, odorless, undetectable to the people living downstream until it was too late. Villages along the river began reporting strange illnesses. Fish stocks declined. Crops failed unpredictably. Soviet scientists monitoring the system knew exactly what was happening, even if it wasn't spoken openly. The river was becoming a sacrifice zone. In the early years, this was tolerated. Secrecy protected the program. The Cold War rewarded results, not restraint. But as reactor power levels increased and operations expanded, the scale of contamination grew impossible to ignore. What had once been a temporary shortcut was turning into a permanent disaster. And that disaster flowed past settlements that had no idea a nuclear reactor existed upstream. By the late 1,950 seconds, even within the Soviet system, this approach had reached its limit. Engineers understood the core problem. Once-through cooling was simple, but it treated the environment as disposable. Every increase in reactor power meant more heat and more contamination dumped into the river. The next reactor could not be built this way. Not politically, not environmentally, and not technically. At the same time, the city above the mountain was growing faster than anyone had predicted. What had started as a controlled workforce turned into a full-scale urban center. Apartments multiplied, schools expanded, hospitals were added, factories demanded electricity, and every new building connected itself to the heating grid. The reactor below was no longer just a military asset. It was infrastructure. That changed the equation completely. Dumping radioactive water into the river wasn't just poisoning the environment anymore. It was poisoning the same region the reactor was now expected to support. For Soviet planners, this created a rare and dangerous conflict between objectives. They needed more plutonium. They needed secrecy. They needed safety. And now, they needed efficiency. For the engineers tasked with designing the next reactor, the message was clear. The old solution was forbidden. The new reactor had to meet three conditions simultaneously. First, it had to produce weapons-grade plutonium at industrial scale. There would be no reduction in output. Second, it could not release radioactive coolant into the river, not directly, not indirectly. And third, it had to use its enormous waste heat productively, because wasting heat while a city froze above was no longer defensible. This was not an incremental upgrade. It was a complete reversal of philosophy. In traditional reactor design, waste heat was the enemy, something to get rid of as quickly as possible. Cooling systems existed to remove it, discard it, and keep the core stable. Here, waste heat became the most valuable output. That alone created a design paradox. A reactor optimized for plutonium production operates very differently from one optimized for electricity or heating. Power fluctuations that might be acceptable in a weapons reactor could be disastrous for a city heating network. Heat delivery had to be stable, predictable, continuous. Shutting down the reactor for maintenance was no longer a purely technical decision, it was a civic one. And yet, the reactor still had to operate inside a mountain. That constraint had not changed. There would be no massive cooling towers rising into the sky, no large reservoirs for thermal dissipation, no open-air redundancy. Everything had to fit underground. Every pipe, every pump, every heat exchanger. And if any one of those systems failed, there would be nowhere for the excess heat to go. Soviet engineers now faced a problem they had never been trained for. They weren't just designing a reactor anymore. They were designing an artificial ecosystem, one that had to balance nuclear physics, mechanical engineering, chemistry, climate extremes, and human survival, all with 1,960 seconds technology, all in secrecy, all underground. And they had to get it right the first time. Because once the reactor was sealed inside the mountain and connected to the city above, reversing course would be nearly impossible. The old approach, dumping heat and contamination into a river, had bought time. But time was up. What came next would determine whether this city survived its winters, or whether the reactor that powered the Cold War would become its greatest liability. At some point, Soviet engineers realized they were asking the wrong question. They weren't trying to figure out how to cool a reactor. They were trying to figure out how to not waste it. In most nuclear facilities, heat is treated as a liability. The entire purpose of a cooling system is to remove thermal energy from the reactor core as quickly and safely as possible, then discard it into the environment, into air, rivers, or cooling towers, where it stops being a problem. That logic made sense when a reactor's only mission was plutonium production, but it made no sense anymore. Because above this reactor, an entire city was freezing. By the early 1,960 seconds, winter temperatures in central Siberia regularly stayed below -30 degrees Celsius for months at a time. Buildings were designed around continuous heat delivery. Pipes ran through walls that would crack if they froze. Heating systems were not optional add-ons. They were structural. If the heat stopped, the city didn't just get uncomfortable, it failed. So, engineers began to think differently about the reactor's thermal output. Instead of asking how to dump 1,400 megawatts of heat, they asked how to capture it, how to move it, how to control it, and how to deliver it to tens of thousands of homes without ever letting it destabilize the reactor core. This was not a minor adjustment. A plutonium production reactor was never designed to be a municipal utility. Its power output fluctuated. Fuel elements were swapped frequently. Shutdowns happened without regard for civilians. Heat was variable and, in many cases, violent. A city, by contrast, demanded stability. Radiators didn't care about neutron flux. Apartment blocks didn't tolerate thermal swings. Hospitals needed predictable temperatures day and night. What Soviet engineers were now proposing was a single system that had to satisfy both. A machine optimized for nuclear reactions, and a network optimized for human survival. The breakthrough came when engineers stopped thinking of cooling as a single process. They separated it. Instead of one system that removed heat and threw it away, they designed a chain, each link doing a specific job, each one isolating risk from the next. At the center of this chain was a simple but radical idea: closed-loop cooling. In the earlier reactors, water entered the core once and left contaminated. In the new design, the water that touched the fuel would never leave the reactor complex. Ever. This primary cooling circuit would circulate endlessly, absorbing heat from the fuel channels and carrying it to heat exchangers but never escaping into the environment. That decision alone eliminated the river contamination problem. But it created another challenge, because now all of that heat had to go somewhere else. That somewhere became the secondary cooling circuit. Instead of radioactive water flowing out of the reactor, clean water flowed around it, never touching fuel, never becoming contaminated. Heat passed through metal walls inside massive heat exchangers, transferring energy without transferring danger. This secondary water could then be used safely. And this is where the reactor's mission changed forever. The heated secondary coolant was routed into steam generators. There, it flashed into high-pressure steam hot enough to drive turbines and generate electricity. That electricity powered the reactor complex itself and the city above. But the engineers didn't stop there. After passing through turbines, the steam still carried enormous amounts of usable heat. In a conventional power plant, that heat would be condensed and discarded. Here, it was redirected. Pipes carried that steam directly into the city's district heating network. As it condensed, it released its remaining thermal energy into residential buildings, schools, hospitals, and factories. Only after delivering its heat to the city did the water return to the cooling cycle. This wasn't just efficient, it was necessary. By design, the reactor would now supply roughly 75% of the city's heating needs. The remaining heat came from auxiliary boilers, but without the reactor, the system could not sustain Siberian winters. Waste heat had become survival heat, and that changed everything about how the reactor had to operate. Suddenly, reactor stability mattered more than raw output. Power fluctuations had downstream consequences. A spike in reactor temperature wasn't just a technical anomaly, it could overload heating networks. A sudden reduction in power could leave neighborhoods cold within hours. The reactor was no longer an isolated machine. It was the beating heart of a living system. And that system had no tolerance for mistakes. Engineers now had to design for conditions no military reactor had ever faced. Winter loads were enormous. Heat demand peaked when the river was at its coldest and flow rates dropped. Summer loads fell, but the reactor still needed to operate for plutonium production. Balancing those cycles required precise control. Too much heat, and the system risked overpressure. Too little, and the city froze. Every component had to work in coordination. Pumps had to maintain steady flow through thousands of fuel channels. Heat exchangers had to transfer energy efficiently without leaking. Steam generators had to produce consistent output without destabilizing the reactor core. And all of this had to function underground, inside a mountain, with limited space and no access to the open air. What Soviet engineers had created was something entirely new. Not just a reactor, not just a power plant, but a closed, self-contained thermal ecosystem where nuclear physics, mechanical engineering, and urban infrastructure were permanently linked. This was the moment when the reactor stopped being just a weapons factory. It became a utility. And utilities don't get to fail. Because once a city grows around them, once families depend on them, once hospitals and schools and apartment blocks rely on them, shutting them down is no longer a technical decision. It's a moral one. The reactor could no longer be allowed to waste heat. It couldn't dump it into a river. It couldn't release it into the air. It had to capture it, control it, and deliver it day after day, year after year. And that decision set the stage for the most dangerous part of the entire system. Because capturing heat is one thing, but controlling it inside a mountain, through Siberian winters, with graphite cores and aluminum fuel channels, would require engineering solutions no one had ever attempted before. And if any one of them failed, the consequences would not stop at the reactor. They would spread through the city above. They didn't solve one problem. They solved 3 different ways the reactor could die. Because underground, inside a mountain, failure doesn't behave the way it does on the surface. Heat can't vent upward. Steam can't escape into open air. Every mistake becomes trapped, sealed inside rock. So, Soviet engineers didn't chase a single perfect solution. They designed the reactor as if its worst day was guaranteed to come. The first danger was simple and immediate. If the cooling water ever boiled inside the fuel channels, the reactor would not fail slowly. It would fail fast. The core of this reactor was built for plutonium production. Natural uranium sat inside thousands of vertical channels, bombarded by neutrons, releasing enormous heat. At full power, the reactor produced more than 1,000 megawatts of thermal energy, enough to overwhelm any passive system. The weak point wasn't the uranium. It was the aluminum wrapped around it. Aluminum cladding loses strength quickly as temperatures rise. If cooling slowed or stopped, water inside the channels could flash to steam. Pressure would spike. Fuel elements could deform. Cladding could rupture. And once radioactive material entered the cooling system, the problem would spread everywhere. In an underground reactor, there was no easy way to flush contamination out. Pumps, pipes, heat exchangers, all of it would be affected. So the first rule was absolute. The water could never boil. To enforce that rule, engineers built the primary cooling system to behave more like a force of nature than a utility. Water was kept under high pressure, pushed aggressively through all fuel channels, not allowed to linger, not allowed to slow down. The pressure alone was enough to keep the coolant liquid even as it absorbed extreme heat. And that water never left the reactor building. It never touched the river. It never went near the city. It circulated endlessly in a sealed loop. That mattered because the water became radioactive simply by being near the fuel and neutron flux. Letting it escape would mean spreading contamination through the entire complex. The pumps driving this system were massive. They moved thousands of cubic meters of water per hour. They were the reactor's heartbeat. If that heartbeat stopped, temperatures would rise in minutes. Engineers knew a single pump could never be allowed to decide the reactor's fate, so they designed redundancy as a survival requirement. Multiple pumps, parallel flow paths. Immediate takeover if one unit failed. There was no room for debate or delay. But preventing boiling solved only half the danger, because when that water left the core, it was still carrying all of the reactor's heat. Hot, radioactive, pressurized. It couldn't be dumped. It couldn't be cooled in open air. And it couldn't be used directly, so the heat had to be transferred without transferring danger. That happened inside underground heat exchangers. The primary coolant flowed through thousands of thin metal tubes. On the other side flowed clean, non-radioactive water. Heat crossed the metal walls. Radiation did not. This was the moment where cooling stopped being about disposal and became about control. Because once heat entered the secondary loop, it became safe to use. That heat was routed into steam generators, where it flashed into high-pressure steam. The steam turned turbines, producing electricity for both the reactor complex and the city above. But even after driving turbines, the steam still carried enormous energy. Instead of discarding it, engineers sent it straight into the city's district heating system. Pipes carried steam beneath streets and buildings. As it condensed, it released heat into apartments, schools, hospitals, and factories. Only after delivering that heat did the water return to the cooling cycle. Waste heat had become survival heat. And once that connection existed, the reactor could no longer behave like a weapon factory. Power spikes weren't just technical anomalies anymore. They affected neighborhoods. Power drops weren't just operational events. They meant cold apartments. The reactor had become part of a living system, which introduced the next danger. Because even the best closed-loop system still depends on the outside world. Even sealed systems lose small amounts of water. Heat exchangers still need a cold side. And all of that ultimately depended on the same river that earlier reactors had poisoned. Only now, engineers had to use it without destroying it. The problem was that the river did not cooperate. In winter, ice formed, flow dropped, water temperatures approached freezing. And exactly at the same time, the city's demand for heat peaked. In summer, snowmelt flooded the system. Water temperatures rose. Sediment loads shifted. The river was alive, seasonal, unpredictable. A cooling system designed for a stable river could not survive here. So engineers built an intake system that treated river water as hostile until proven otherwise. Screens removed ice and debris before they could choke flow. Settling tanks stripped out silt. Everything happened underground, protected from the same environment it was fighting. But the most dangerous threat wasn't physical blockage. It was chemistry. The reactor's fuel channels were lined with aluminum. Aluminum corrodes, and corrosion inside a reactor isn't cosmetic. It becomes thinning, pitting. Weak points under pressure. A single corroded channel could rupture and leak radioactive coolant. So, engineers didn't just filter the water, they conditioned it. They adjusted pH. They added corrosion inhibitors. They maintained a narrow chemical window designed to protect aluminum under heat and radiation. This wasn't an optimization. It was the difference between months of operation and decades. And here, Siberia offered a strange advantage. In winter, near-freezing river water created a larger temperature difference across heat exchangers. That made heat removal more efficient if water flow could be maintained through ice. So engineers built systems that could adjust intake rates, adapt to seasonal shifts, and survive extremes. But even with water controlled, pressure maintained, and chemistry stabilized, there was still one danger no amount of water could fully address: the graphite. Inside the reactor, graphite blocks slowed neutrons and sustained the reaction. But graphite absorbed energy. It heated up sometimes to terrifying temperatures. If graphite overheated and oxygen reached it, it could burn. And graphite fires are among the worst disasters in nuclear engineering. They are difficult to extinguish. They spread heat through structure itself, and they can release radioactive material into ventilation systems. Inside a mountain, a graphite fire would turn the entire complex into a sealed furnace. So engineers built a third cooling system, completely separate from the others. They used nitrogen gas. High-purity nitrogen flowed through channels around the graphite, carrying heat away by forced convection. It moved to heat exchangers, cooled, and returned to the core. Nitrogen served two purposes. It removed heat, and it displaced oxygen. By maintaining an inert atmosphere, engineers prevented graphite oxidation entirely. Even hot graphite could not burn without oxygen. This system also provided something more important than cooling: time. If water systems faltered, nitrogen cooling could slow temperature rise. It could buy operators minutes, sometimes longer. In an underground reactor, minutes mattered. By this point, the reactor was no longer a single machine. It was a hierarchy of defenses. If one system failed, another slowed the collapse. If two systems struggled, the third bought time. Nothing was designed to be perfect. Everything was designed to fail slowly. To make all of this work together, engineers filled the mountain with sensors, temperature probes, pressure gauges, flow meters. Data streamed into a central control room. But this wasn't automation as we know it today. Operators worked around the clock, manually adjusting pump speeds, valve positions, and flow paths. They monitored river conditions, adjusted chemistry, watched for subtle signs of imbalance. It was constant vigilance. And then came the test. In 1964, the reactor began operation, not as an experiment, not as a prototype, but as the core of a city's survival. It ran through winters, through floods, through power increases beyond its original design. Engineers learned its limits by living inside them. But starting the reactor was never the hardest part. Keeping it alive year after year was. Because once a city depends on a machine, the most dangerous day is not day one. It's the day something finally wears out. By the time the reactor reached full operation, engineers no longer thought of it as a machine. They treated it like a living organism. Machines can be started and stopped. Organisms have rhythms. And this reactor had one that never slept. Every second, heat was being generated deep inside the mountain. Every second, that heat had to be moved, transferred, balanced, and delivered. There was no pause button. No safe idle state during winter. No moment where the system could relax. Inside the control room, operators didn't just watch gauges. They watched behavior. Small changes mattered. A slight temperature drift in one fuel channel could signal corrosion beginning months before a failure. A subtle pressure imbalance might indicate a pump losing efficiency. A delay in heat transfer could mean scale building inside a heat exchanger. None of these were emergencies by themselves, but together they were warnings. Operators worked in shifts around the clock. They memorized patterns. They learned what normal felt like: the hum of pumps, the vibration through floors, the way temperature curves rose and fell during power adjustments. In winter, the reactor behaved differently. River water entered the system colder. Heat exchangers became more efficient, but ice threatened intakes. Steam demand from the city spiked. Heating loads peaked when daylight was shortest, and temperatures stayed below -30 for weeks. The reactor had to be tuned like a breathing organism: inhale cold water, exhale heat, never too fast, never too slow. In summer, the balance shifted again. River flow increased. Water temperatures rose. Heat demand from the city dropped. But plutonium production continued. The reactor still needed to run. Excess heat had to be managed carefully to avoid overloading secondary systems. Every season forced operators to rethink their assumptions, and every adjustment had consequences. Increase coolant flow too quickly, and pressure transients could stress fuel channels. Slow it too much, and localized heating could develop. Alter water chemistry too aggressively, and corrosion risk changed elsewhere. This was not automation. This was human judgment, exercised thousands of times a day. Maintenance made everything harder. Fuel channels degraded over time. Aluminum cladding wore down under heat, radiation, and chemistry. Eventually, channels had to be replaced. That meant shutting down sections of the reactor, isolating systems, and working inside an environment that was never meant to be friendly. Every maintenance operation carried risk. A valve stuck in the wrong position could alter flow paths. A misread gauge could delay response. And because the reactor was underground, access was constrained. Space was tight. Ventilation was controlled. You couldn't simply open the building to cool things down. Operators learned to think ahead. They didn't ask whether something could fail. They asked when. Pumps were replaced before they failed. Heat exchangers were inspected for microscopic leaks. Sensors were recalibrated constantly. Redundancy was not assumed to be eternal. It was treated as temporary protection. This mindset kept the reactor alive as power levels increased. Over time, engineers pushed the reactor beyond its original design output. From around 1,450 megawatts thermal, it climbed higher, 1,800 megawatts, and at times even more. Each increase was deliberate. Calculations were redone. Cooling margins were reassessed. Pump capacities were upgraded. Heat exchanger performance was measured under real conditions, not theoretical ones. Nothing was taken on faith, because the cost of being wrong was not abstract. It was measured in frozen pipes and dark windows above. The city felt every fluctuation. When power levels were adjusted, district heating systems responded. When maintenance required temporary reductions, backup boilers kicked in. If those boilers failed to keep up, residents noticed. The reactor was invisible to most people, but its effects were everywhere. Steam pipes ran beneath streets. Heat radiated through walls. Entire neighborhoods lived on the assumption that the reactor below would keep working tomorrow, and that assumption was never guaranteed. As years passed, the world outside the mountain changed. The Cold War shifted. Leadership changed. Policies evolved. But inside the reactor complex, the rules remained the same. Keep it running. Keep it stable. Don't let it fail. New generations of engineers took over from the ones who built the system. They inherited not just hardware, but institutional memory lessons learned from near misses, anomalies, and close calls that never reached official reports. Stories passed quietly between shifts. A vibration that almost went unnoticed. A temperature spike caught just in time. A pump that failed seconds after redundancy took over. These weren't celebrated. They were warnings. Because every year the reactor aged, metal fatigued, insulation degraded, control systems became obsolete, spare parts grew harder to source, documentation aged alongside hardware. And yet, the city still needed heat. By the time the Soviet Union collapsed, the reactor had been running for decades. Its original military mission was fading, but its civilian role had become absolute. Shutting it down was no longer just a technical decision. It was political. Where would the heat come from? Replacing the reactor meant building massive fossil fuel plants, new pipelines, new infrastructure projects that cost hundreds of millions and took years. In the meantime, winter kept coming, so the reactor stayed online. Operators kept balancing flows. Engineers kept reinforcing systems. Maintenance crews kept replacing worn components inside a mountain built for a different era. The reactor outlived the country that built it, and with each passing year, the question grew more uncomfortable. How long can a city depend on a machine that was never meant to be permanent? Because the longer it ran, the harder it became to stop. And the more everyone involved understood a quiet truth. The most dangerous phase of this reactor's life was not the beginning, it was the end. When the world decided it no longer wanted plutonium, but the city still needed heat. When the Cold War began to unravel, the reactor did not. Borders shifted, flags changed, ideologies collapsed. But deep inside the mountain, pumps kept turning, valves kept adjusting, and heat kept flowing upward into the city. For the first time since it was built, the reactor's original purpose was fading. The Soviet Union no longer needed more weapons-grade plutonium. Treaties were signed. Stockpiles were frozen. Production targets disappeared from planning documents. But the reactor could not simply be turned off, because by then, it wasn't just a weapons facility. It was the city's heart. Above ground, tens of thousands of people still depended on the same system of pipes and steam. Winters were just as cold. Buildings were just as unforgiving. And the heating network had been designed around one assumption that had never been tested. The reactor would always be there. Shutting it down meant more than ending plutonium production. It meant replacing the single largest source of heat for an entire city almost overnight. That replacement did not exist. There were auxiliary boilers, but they were never meant to carry the full load through Siberian winters. They were backups, not substitutes. Scaling them up would require massive fuel supplies, new infrastructure, and years of construction. And years were something the city did not have. So the reactor kept running. In the early 1990 seconds, its mission quietly changed. Officially, it was no longer producing plutonium for weapons. Instead, it operated as a civilian power and heating plant, supplying electricity and district heat to a growing population. In practice, nothing about its operation became easier. The reactor was aging. It had been built with 1960 seconds technology, designed for a world that assumed constant maintenance, abundant expertise, and unquestioned funding. Now, funding was uncertain. Spare parts were harder to source. Experienced engineers retired or left. And yet, the system could not tolerate neglect. Pumps still had to be maintained. Heat exchangers still had to be inspected. Fuel channels still degraded and needed replacement. Every year added wear to systems that had already exceeded their original design life. At the same time, international pressure was growing. Western governments wanted the last plutonium production reactors shut down permanently. Environmental groups raised concerns. Safety experts questioned the wisdom of keeping an aging underground reactor running indefinitely. But no one could answer the simplest question. If the reactor shuts down, where does the heat come from? That question turned a technical problem into a diplomatic one. In the mid-1990 seconds, negotiations began between Russia and the United States. The goal was clear: end plutonium production once and for all. The obstacle was just as clear. The city above the reactor could not survive without a replacement heat source. The solution, on paper, was straightforward. Build new fossil fuel cogeneration plants capable of matching the reactor's thermal output. Construct pipelines to integrate them into the existing district heating system. Transition the city gradually, without interrupting heat during winter. In reality, it was anything but simple. The cost ran into the hundreds of millions. Construction timelines stretched. Equipment procurement stalled. Bureaucratic delays piled up. Every missed deadline meant another winter where the reactor had to keep running. Meanwhile, operators continued their work underground. They were no longer maintaining a strategic asset. They were maintaining a liability everyone depended on, but no one wanted to own. The reactor had become politically awkward, too dangerous to celebrate, too essential to abandon. Each year it ran, it bought time for replacement infrastructure to catch up. Each year it ran, it also aged further, increasing long-term risk. The irony was unavoidable. A machine built for war had outlived the war, and now peace depended on it. By the early 2000s, agreements were finally signed. Funding was secured. Construction began on replacement plants designed to take over the city's heating load. But even then, the transition could not be rushed. Pipelines had to be tested. Boilers had to be commissioned. Control systems had to synchronize with an existing network built around nuclear heat. One mistake during the switchover could leave the city without heat in the middle of winter. So the reactor stayed online, quietly filling the gap. It ran while negotiations dragged on. It ran while construction stalled. It ran while the world debated its fate. Operators kept balancing flows. Engineers kept replacing worn components. Maintenance crews kept systems alive inside a mountain that had already held them for decades. The reactor had become something no one planned for. A bridge, not between two technologies, but between two eras. An era where nuclear weapons drove engineering decisions, and an era where the survival of ordinary civilians dictated them instead. And as the replacement plants finally neared completion, one truth became impossible to ignore. The hardest part of this story was never keeping the reactor running. It was figuring out how to stop it, without freezing the city it had kept alive for generations. Shutting down the reactor was never about turning a key. It was about timing. Because in Siberia, timing decides whether pipes freeze or survive, whether buildings crack or endure, whether a city wakes up warm or doesn't wake up at all. By the late 2000s, the replacement heating plants were finally nearing completion. Coal-fired cogeneration facilities stood ready to take over the load the reactor had carried for decades. New boilers were installed, turbines were tested, pipelines were connected to the same district heating network that once depended entirely on nuclear heat. On paper, the transition looked clean. In reality, it was terrifying. The reactor could not be shut down abruptly. Doing so would collapse heat supply faster than backup systems could respond. Thermal inertia worked both ways. What kept the city warm also made change slow and dangerous. Engineers had to choreograph the shutdown like surgery. Reactor power would be reduced gradually. As nuclear heat dropped, fossil fuel systems would ramp up in perfect synchrony. Pressure, temperature, and flow rates across the heating network had to remain stable the entire time. There was no margin for error. A sudden drop in steam pressure could cause condensation in pipes not designed for it. Ice formation could begin in minutes. Once ice formed, restarting flow was not guaranteed. Winter loomed over every decision. Schedules were built around seasons, not calendars. No one wanted to risk a switchover during peak cold. The shutdown window had to be chosen carefully, when temperatures were high enough to forgive mistakes, but low enough to test real demand. Inside the mountain, operators prepared for the end of a lifetime routine. They inspected systems that had run almost continuously since the 1,960 seconds, pumps that had been rebuilt again and again, valves polished by decades of use, heat exchangers that had quietly moved unimaginable energy without ever being seen by the people they protected. For many of the engineers involved, this reactor had defined their careers. Some had spent decades keeping it alive. Now they were being asked to let it go. On April 15, 2010, the final phase began. Reactor power was stepped down methodically. Fuel elements were withdrawn according to procedures refined over years of planning. Cooling systems remained active, removing residual heat as the nuclear reaction slowed. Above ground, the city felt nothing. Radiators stayed warm, lights stayed on. Steam continued to flow through the same pipes it always had. That was the goal. No celebration, no announcement, no dramatic moment, just continuity. When the reactor finally shut down completely, nothing visible changed for the people living above it. Streets didn't go cold. Buildings didn't go dark. Life continued. And that was the greatest success of all. Because a machine that once decided whether a city lived or froze had been removed without the city ever noticing. In the months that followed, decommissioning began. Spent fuel was removed. Systems were drained, decontaminated, and isolated. Sections of the underground complex were sealed for long-term management. The mountain that had hidden a reactor for half a century went quiet. For the first time in more than 50 years, there was no nuclear heart beating beneath it. The AD and AD-1 reactors had already been shut down years earlier. Now, the last one was gone. What remained was infrastructure shaped by an era that no longer existed, and a city that had survived it. The reactor had started life as a weapon factory. It ended as a bridge that kept civilians alive while the world changed around them. And in the end, its greatest achievement wasn't the plutonium it produced. It was the fact that it could finally be turned off, without killing the city it had been forced to save. Long after the reactor shut down, the mountain remained. Deep inside it, tunnels still run through granite. Pipes still line walls. Caverns built for machines that no longer exist wait in silence. Decommissioning will take decades. Some parts may never be touched again. But the reactor's legacy didn't end when its pumps stopped. What Soviet engineers built inside that mountain quietly changed how the world thought about nuclear energy. The closed-loop cooling systems they pioneered, separating radioactive primary circuits from secondary heat extraction, became the foundation of modern reactor design. Today, pressurized water reactors around the world use the same basic principles. So do district heating systems that deliver nuclear heat safely to civilian cities. What began as an improvised solution in Siberia became a template. That doesn't erase the cost. The early reactors polluted rivers. Forced labor built the tunnels. Plutonium fed weapons that threatened civilization itself. None of that disappears because the engineering worked. But it does reveal something uncomfortable. The same machine that made weapons possible also kept a city alive for half a century. Not because it was meant to, but because people adapted it to be. This reactor was never supposed to be permanent. It was designed for urgency, not longevity. And yet it outlived the war that created it, the country that funded it, and the ideology that justified it. In the end, its most important role had nothing to do with bombs. It was heat, reliable, invisible, taken for granted until the day it was gone. When the reactor finally shut down, the city did not collapse. Life went on. New plants took over. The transition worked. That success was quiet, and maybe that's the point. The most remarkable thing about this reactor is not that it was built inside a mountain, or that it ran through Siberian winters, or that it produced plutonium in secrecy. It's that for decades, ordinary people lived normal lives above it, never thinking about the machine beneath their feet that made those lives possible. The mountain still stands. And somewhere inside it, the memory of a reactor that refused to fail remains a reminder that engineering doesn't just shape wars. Sometimes, it decides whether cities survive them.